Hello, welcome to another mathematics video on ordinary differential equations. Once again, we're now going to look at another Hermite ordinary differential equation, and I'll just write down the title. Basically, we're going to solve the Hermite ODE, meaning ordinary differential equation, which is, I'll write it down in prime terms. So y double prime minus 2x y prime plus 4y equal to 0. Well, how do we solve this? Well, if you've seen my last video, you will know that and I'll write this down in blue. This is of the form y double prime minus 2x y prime plus 2ny equal to 0. So we can see that the 2n is equal to 4, which is this term here. That is what the 2n is equal to, right? So, solving this simple equation here, we find that n equals 2. Because if n is 2, 2n becomes 4, right? So we're going to solve what we will call equation 1. We're going to solve equation 1 for n equals 2, when n equals 2. So now let's write this down. The first linearly independent solution is obtained. It's not very clear writing, but many apologies. So the first linearly independent solution is obtained from the formula y equals minus 1 to the n e to the x squared times the nth derivative, whoops, just press something there, the nth derivative of e to the minus x squared, okay? So that's how we find our first linearly independent solution. And of course, what I didn't say in the other video is that this, all the first linearly independent solutions to whichever set of Hermite polynomials you have are Hermite polynomials. So whatever Hermite ordinary differential equations you have, the first linearly independent solutions to those equations are Hermite polynomials. I think I got my syntax is a bit mangled there, but many apologies. Anyway, let's crack on and find the first linearly independent solution to equation 1. So, well, we know that n is equal to 2. N is equal to 2. So we substitute n equals 2 into equation 2. So we'll call that equation 2. So the first linearly independent solution is, I should really said when n is equal to 2, is y equals minus 1 squared times e to the x squared times the second derivative of e to the minus x squared, right? So to work this out as a Hermite polynomial, we have to calculate the second derivative of e to the minus x squared. So I'm going to do this in stages. You might know how to do it straight off, and if you can, then that's great, and you can skip forward in the video. But for those who aren't sure what to do here, I shall quickly take you through that. So we've got y equals minus 1 all squared e to the x squared times the second derivative of e to the minus x squared. Okay? Well, minus 1 all squared is just 1. So we'll just leave that as it is. So we've got e to the x squared. We've got minus 1 squared, which is 1. So 1e to the x squared times the derivative of, well, we want to find the first derivative first of e to the minus x squared, right? And if we do that, we get, well, we'll write it down properly, e to the x squared times d by dx of. Now we've got to find the first derivative of e to the minus x squared. Well, that is simply minus 2x e to the minus x squared, right? So we've got y equals e to the x squared times what is now the first derivative of 2x e to the minus x squared, right? Oh, and by the way, we've got a minus sign, which we can bring out here, right at the very front. So we've got minus e to the x squared times d by dx of 2x e to the minus x squared. And if you do that second differentiation, d by dx, of this term in brackets, well, we still have the minus e to the x squared on the outside of the brackets. Let me just make that a little neater. Right, okay. We'll put brackets there as well. So when we differentiate 2x e to the minus x squared, we get 2e to the minus x squared minus 4. Well, I was going to write it straight down, but I shouldn't miss any steps out. So we differentiate the 2x first. We're left with 2. And obviously we write down the e to the minus x squared. So we've got 2e to the minus x squared. And then it's plus, this time we'll leave the 2x as it is, and we differentiate the e to the minus x squared. So we get minus, I'm just wondering how I can fit this on, minus 2x e to the minus x squared. I can't really fit that on, but let's go on to the next page and do it properly. So we've got y equals minus e to the x squared times, in brackets, 2e to the minus x squared plus 2x times minus 2x e to the minus x squared. So there we are. We were faffing around before, weren't we? And anyway, we've written it down properly now, and this can be simplified. So before I do anything else, I'm just going to cancel all the exponentials. Because what we're effectively doing is multiplying out this e to the x squared by all the e to the minus x squared terms in the bracket. So what we're left with is y equals minus, in brackets, 2 minus 4x squared, right? And that can be simplified to give y equals 4x squared minus 2. And that is indeed the a Hermite polynomial for that for the case of the Hermite equation when n is equal to 2. Right? That is the first linearly independent solution is a Hermite polynomial for the case when n is equal to 2. Right. We want to find the general solution. Right, so how do we do that? Okay, well, let's just go on to the next page. So we know that y equals 4x minus 2. Is it 4x minus 2? 4x squared minus 2. Let's check we've got that right. Yeah, we have. So y2, the second linearly independent solution, is equal to y1. Let me distinguish that 1 from the y. There we are. So it's y2 is equal to y1 times, in brackets, the integral of e to the minus the integral of p dx divided by y1 squared dx plus c. Well, once again, I don't know if you've seen the previous video, but you should hopefully be able to work out what P actually is by writing down the equation, again, the original equation 1, the Hermite ordinary differential equation. So the equation is, we'll just write it down for reference, y double prime minus 2x y prime plus 4y equals 0. So we can see from this equation that, as before, that minus 2x is what p actually is. So p here in the exponent of the exponential is minus 2x. So y2, well, maybe I should write that down more clearly. So I'll write down in green, e equals minus 2x. P equals minus 2x. And also, we know what y1 is. y1 equals 4x squared minus 2. We need both of those pieces of information to solve for the second linearly independent solution and therefore to find the general solution. So let's now move on to the next page. So I'm going to write down again those two pieces of information. So we've got y1 is equal to 4x squared minus 2. And we've got p equal to minus 2x, right? From the original Hermite differential equation. So y2 becomes, and if you remembered, it was of the form y1 times, in brackets, the integral of e to the minus the integral of p dx divided by y1 squared dx plus c. And I'm just repeating that. Let me see if I can squash it more onto the left-hand side, and then I can use some of the space towards the right, and then we're not, then we can see things more clearly. So, right, now we know what y1 is. This y1 here is this term here, 4x squared minus 2. So we write down the 4x squared minus 2. And I'll put brackets around that. And that is multiplied by, and I don't know whether I will be able to squash this all on, but we'll try. So we've got inside the brackets an integral of e to the minus integral of p dx. Well, p is minus 2x, then we've got our dx term there, and underneath we've got in the denominator of this integral fraction, we've got 4x squared minus 2 all squared. Then we've got our dx term, and we've got a constant somewhere there. Right. So maybe I should make it a little clearer if I can. I hope that's clear for you, but basically that's what you do. And if you proceed with the algebra, you get 4x squared minus 2 times, and we've got the integral of the exponential. So we've got e to the integral of 2x dx over 4x squared minus 2 all squared dx plus c. Right, so the integral of this this exponential bit here of the exponent is quite easy to do. It's just the integral of 2x dx, which is just x squared. So we'll write all this down again, but having done the integral there. So we'll go on to the next page, and we've got y2 equals 4x squared minus 2 outside the brackets, and we've got the integral of e to the x squared over 4x squared minus 2 all squared, and we've got a dx term there and a constant. Right? So let's just, there we are, let's just make a bit more space. Right. Now, this is the difficult part because we have to work out the this. We have to integrate this on the right hand side of this equation in order to get the explicit form of the second linearly independent solution. So this is again very, very complex to do, and it's easier just to use software which can come up with a solution immediately for this. So if we use software, some free software that will be able to do this is Python. So Python may be able to come up with the integral of what's on the right hand side here. So if we use our software to find the solution, we've got y2 equals 4x squared minus 2 times, and what colour shall I do this in? I'll do this in blue. Right, so we've got the bracket there, and all of this inside the brackets works out to give the root of pi over 16 times the imaginary error function of x. In fact, actually, I'm just going to try and condense my letters because I'm taking up a lot of space, and I want to make space. So we've got the imaginary error function of x minus x e to the x squared over 8 2x squared minus 1, and then we've got a constant. Right. So that, as it stands, is our second linearly independent solution. Now, I might have been a bit confused about the next part in previous videos because the general solution, and I'm going to write this in red, the general solution is found from adding y1 to y2, but by putting constants in as well. So, for example, the general solution is equal to some constant a times y1 plus some constant b times y2. In fact, I'm going to call these constants something else. I'm going to call them, let me see, right, so I'm going to call this constant k1 and that constant k2. So we've got y equals k1 y1 plus k2 y2. So this means that y is equal to k1 times y1. Well, we know what y1 is. I'll go back to where we found y1. Y1 is this term here, 4x squared minus 2. And I think we've identified it down here as such. And then we've used it in the solution of the second linearly independent solution. So we've got k1 times 4x squared minus 2, right, plus k2 times, in brackets, 4x squared minus 2 times the root of pi over 16. Oops, not a very good 6, is it? Right. That's supposed to be a 16. A function of x. And I'm going to have to go on to the next line. So we've got minus x e to the x squared, all divided by 8 times 2x squared minus 1 plus c. Now, this can be simplified. I'll do that for you. So we've got y equals k1 times 4x squared minus 2 plus k times 4x squared minus 2 times root of pi over 16, imaginary error function of x, minus x e to the x squared over 8 times 2x squared minus 1. We'll close the brackets there, and then we'll multiply that constant there. We'll just underline it in red. We're multiplying that constant there by this term here, and obviously we're multiplying that by k2, so we get, and I'll keep this in red, plus k2 4x squared minus 2 times c. So let's have a look and see if we've done that right. Yeah, okay. Now, you'll be able to observe that in fact, that actually should be K2 there, shouldn't it? Right. So we've got a solution that can be tidied up a little bit more. And what you recognise is that, what you will hopefully recognise is that these two terms are the same, so they can be combined. What we say is that the second term gets absorbed into the first term. So actually, what we get now is y equal to, well, let me just write that out. If you've got k1 times 4x squared minus 2 plus k2c 4x squared minus 2, then you can simplify this by factorising everything out as such, so that you get k1 plus k2c all multiplied by 4x squared minus 2. So k1 plus k2c all multiplied by 4x squared minus 2. And this k1 plus k2c you can just represent by the letter a. A times 4x squared minus 2. So let me just make a little more room down here. The general solution can therefore be written as y. Let me write that in black. So the general solution is y equals a times 4x squared minus, let me just get that x a little more convincing than it was. So we've got a times 4x, let me just get that, yeah, there we are, 4x squared minus 2 plus all of this here, plus all of that. Well, we just change the K2 to the letter B. It doesn't matter what you call it. I'm just trying to be consistent with my constants. So we've got B times 4x squared minus 2 times, in brackets, pi over 16, imaginary error function of x. Let me just imaginary error function of x minus x e to the x squared over 8 2x squared minus 1 and close brackets. Now we can actually just tidy that up a little bit more, because we can actually factorise out this term and this term. So I'll quickly do that, and what we're left with is y equals 4x squared minus 2 times, in brackets, a plus b, and I have to go back on this one, times, in brackets, root of pi over 16 times the imaginary error function of x minus x e to the x squared, all divided by 8 times 2x squared minus 1. 2x squared minus 1. Woo! Gremlins in the works. And that is the general solution to the Hermite ordinary differential equation when n is equal to 2. I'll write that down for you. This is the general solution to the Hermite I can't get my handwriting decent, can I? Anyway, Hermite ODE. This is the general solution to the Hermite ordinary differential equation when n equals 2. Namely, y double prime minus 2x plus 4y equals 0. Okay? So that just about concludes this video for that particular Hermite polynomial when n is equal to 2. So I hope you have enjoyed that video and that you're looking forward to future videos that I make and that you will come back and watch more of my videos. And until then, I shall bid you farewell and say goodbye for now. So thank you very much for watching. Bye bye.